Following question is about electrochemistry, and the question reads that lead 2 chloride PbCl2 can be used in the manufacture of some types of colored glass. And then it reads that PbCl2 is sparingly soluble in water. So this is one information that the concentration of lead ions in water is not going to be very high because PbCl2 is not very soluble. So the lead ions concentration in a saturated solution of PbCl2 can be estimated by measuring the cell potential Ecell of the following cell. So he's given you a cell along, so it's a complete cell. On one side I have, he's trying to measure the Ecell of the following cell, and he's asking the spaces below identify the four letters A to D above in the A to D in the above diagram. What do they represent? So the first thing is there's hydrogen gas in this gas jar. So the solution must contain H plus 1 ions. So this C over here would be H plus 1 ions in aqueous state. So the solutions over here are H plus 1 ions. This B over here would be a platinum electrode. So this left hand electrode is a standard hydrogen electrode. So this B over here is platinum electrode. On the other hand, I have another electrode where the solution has, it's a saturated solution of PbCl2. So the solution contains Pb2 plus ions. So this D electrode would probably be made out of lead. It would be made out of lead. So D would be Pb. And the last thing here, which is A would probably be a voltmeter. So this is a voltmeter. So what this diagram is doing is that this is your standard hydrogen electrode. Standard hydrogen electrode has zero potential. It's used as a reference, and we're trying to calculate the electrode potential of a lead ion electrode. So the reaction, the equilibrium reaction that would be going on at this electrode would be the one with that could be represented by this equation. That lead ions would be gaining electrons to form lead, and vice versa, lead would be losing electrons. So there would be an equilibrium reaction established on the right hand electrode, the one that is given over here, and the equation for that equilibrium reaction would be this, which I've written over here. In the next part of the question, part B, the question states that in a saturated solution of PbCl2, the concentration of PbCl2 is given. It's given as 3.5 into 10 raised to minus 2. So this concentration of, since PbCl2 contains lead ions, the concentration of aqueous lead ions is lesser than 1 mole per decimeter cube. As you can see, it's only 3.5 into 10 raised to minus 2 mole per decimeter cube. The standard conditions, the electrode potentials are calculated under standard conditions where the concentration is 1 mole per decimeter cube. So in part 1, you asked the E0 for lead 2 plus lead electrode is minus 0.13 volts. Now this is the standard electrode potential. The standard electrode potential is for ions or solutions having a concentration of 1 mole per decimeter cube. So the equation at the electrode was this one. This was the equation. Now if lead ions over here have a concentration that is less than 1 mole per decimeter cube, he's also given you the value of this electrode potential. The standard electrode potential is given as minus 0.13 volts. But now the problem is your electrode is not under standard conditions. The concentration is only 3.5 into 10 to the minus 2 mole per dm3, which means the lead ions concentration is a lot lesser. So if the lead ions concentration is less, that would mean that the equilibrium would shift to the left. And if it shifts to the left, it's going to produce a lot of electrons and the electrode would become more negative. So if it shifts to the left, the E electrode becomes more negative, which means it becomes lesser than minus 0.13 volts. It becomes more negative, more electrons are produced. And the only option for that is it's going to be this one, minus 0.17 volts, because all the other ones, these electrode potentials are more positive. So we needed a value that is going to be more negative than minus 0.13, which is going to be minus 0.17. And the answer that you're going to write, explain your answer, you're going to mention the equilibrium, and you're going to say that equilibrium shifts to the left if lead ions concentration decreases, because for the simple reason that lead ions or PbCl2 is not very soluble, so the concentration is very less. So if the lead ion concentration decreases, which would then decrease the electrode potential, and the electrode potential would become more negative. So if the standard electrode potential was minus 0.13 volts, under non-standard conditions, under these conditions, the electrode potential is going to be less than minus 0.13 volts, which is going to give you minus 0.17 volts. In part C of the question states that behavior of PbCl2 and SnCl2 towards reducing agents are similar, but the behavior towards oxidizing agents are very different. What that basically means is that he's saying that PbCl2 and SnCl2 towards so PbCl2 and SnCl2 towards reducing agents are similar. So their behavior towards reducing agents. Remember, reducing agents, what do reducing agents do? What reducing agents are going to do is they're going to reduce Pb2 plus. So they're going to reduce PbCl2 and SnCl2 have two ions in them. One is Pb2 plus and the other one is Sn2 plus. So their behavior towards reducing agents are very similar, which means that when they are reacting with reducing agents, both of them, they will have a tendency to get reduced, or they have a similar tendency to get reduced. So what does reduction mean? Reduction means gain of electrons. So I'm going to look at the data booklet and figure out an equation where either lead ions or Sn2 plus, they're getting reduced. So I have to refer to the data booklet. And here's my data booklet, and I'm going to look for equations where Pb2 plus or Sn2 plus are getting reduced, which means that they are gaining electrons. So if you search for the electrode where either of them are gaining electrons, then you're going to come across this equation where Pb2 plus is gaining 2 electrons to form lead, and the E naught for this is given as minus 0.13 volts. And you're going to look up for the other equation where Tin2 plus is gaining electrons and is getting reduced. And if you look at that equation, it's coming out to be minus 0.14 volts. So one thing that you would notice is that the two values are very similar. They're almost the same, which means that the tendency for lead ions to gain electrons is pretty much the same as the tendency for Tin2 plus to gain electrons. So if lead ions get reduced with one substance, then Tin2 plus ions would probably get reduced with that substance as well, because the E naught or electrode potentials are not very different. They're almost exactly the same. So when I'm writing the answer to this question, I'm going to quote the two electrodes with either lead ions or Tin2 plus ions. They're both getting reduced, they're gaining electrons. And I'm going to quote the electrode potential values. One has a value of minus 0.13 volts, the other one has a value of minus 0.14 volts. So they're pretty much the similar. So I'm going to add a comment that since the reduction potentials or electrode potentials are very similar, then they have equal tendency to get reduced when it comes to reacting with reducing agents. So to explain this, I've written that since electrode potentials for reduction of Tin2 plus or lead2 plus ions are very similar, hence the behavior towards reducing agents are also very similar. Now moving to the next part. So that was the explanation. What we did was illustrate this comparison by quoting and comparing relevant E naught values for the two metals and the ions. And so we've explained this why lead, PbCl2 and SnCl2 have similar behavior towards reducing agents. Now moving to the next part, that is that the behaviors towards oxidizing agents are very different. So the behavior towards oxidizing agents are going to be very different. So we need to explain why the behavior towards oxidizing agents are very different. So I've written down the statement that the behavior, lead ions and Sn2 plus, towards oxidizing agents, the behavior is very different. And we need to explain why they're different. So when they're reacting with oxidizing agents, that would mean that they're getting oxidized. And what does getting oxidized means? That they are losing electrons. So I'm going to refer, so they're losing electrons. So I'm going to refer to the data booklet now. and figure out reactions or electrodes in which they are losing electrons. So I've opened the data booklet and I've marked equations where or electrodes where lead ions and Sn2 plus are losing electrons. And remember, if you look at the data booklet, in the forward direction, these are reversible reactions. In the forward direction, Pb4 plus is gaining electrons, but in the reverse direction, lead 2 ions are losing electrons. Similarly, in this reaction over here, tin 2 plus ions are losing electrons. You can also note that lead ions, it has a very high potential. Remember, very high potential indicates that the element has a higher tendency to gain electrons rather than lose electrons. And this one has a relatively low tendency, a low potential, which means that it has a higher tendency to lose electrons, whereas this has a higher tendency to instead gain electrons. So because the values are very different, so the behavior as towards oxidizing agents where they get oxidized, where they lose electrons, lead 2 ions also losing electrons, the behavior would be very different because of the different E0 values. So I've copied the two electrodes. Lead 2 ions losing electrons would be more difficult because it has a very high E0 value. Higher potential means that it has a higher tendency to gain electrons. So it's going to be very difficult to oxidize lead 2 ions. Whereas tin 2 plus ions has a much lower E0 value, which means that relative to lead 2 plus ions, this ion over here has a higher tendency to get oxidized. So in my answer, this is what I'm going to write, that because of the higher potential, lead 2 ions would be difficult to oxidize, whereas Sn2 plus ions would be more difficult to oxidize. So in my answer, I'm going to quote these electrode potentials, and I'm going to write that because of higher E0 value for the lead 4 plus, lead 2 plus electrode, Pb2 plus ions would be difficult to oxidize compared to tin 2 plus, as Sn4 plus, Sn2 plus electrode has a much lower E0 value. In the next part, I need to write a balanced molecular or ionic equation. In each case, suggest a reagent to carry out each of the following reactions. And the first one is the reduction of PbCl2. What that means is I need to reduce lead ions. I'm basically talking about this electrode that we were discussing previously as well, having a value, E0 value of minus 0.13 volts. So I need to reduce lead ions, which means that this reaction should go in the forward direction. Now remember that the electrode that gains electrons, in this case I want this electrode to gain electron. I want this to go in the forward direction. Remember that the electrode that gains electron is always going to be the higher potential. Higher potential, or the more positive potential electrode, is always the one that would be gaining electrons. So higher potential would gain electrons. So what I'm looking for is my other reagent is going to be something that has a lower potential compared to minus 0.13 volts, because I know that higher potentials gain electrons, and I want lead 2 plus ions to get reduced. I want it to gain electrons. So I want some other thing that should be losing electrons. And so lower potential is the one that would lose electrons. So I'm basically looking for something that has a lower potential. I want an electrode that has a lower potential so that it would lose electrons. So I'm going to go and look in the data booklet and see, figure out an electrode that has a lower potential compared to this minus 0.13 volt. So if you refer to the data booklet, you would see a number of electrode potentials that have a value that is much lower than minus 0.13 volts. So for example, I have this aluminium electrode, aluminium ion and aluminium electrode, that would be one. Or it could be the barium ion electrode given over here. So it could be any of the electrodes that has an E0 value of less than minus 0.13 volts. So I've picked the aluminium ion, aluminium electrode that has a much lower value of minus 1.66. So low potential has a tendency to lose electrons or produce electrons. So this reaction would go in the backward direction. As aluminium would lose electrons, it has a very high tendency to lose electrons, whereas lead ions would gain electrons to form a lead. And what I need to now do is I need to construct an overall balanced reaction. the first thing I need to do is I need to balance the number of electrons that are being lost and gained. The number of electrons that are being gained are 2 electrons, whereas the number of electrons that are being lost by aluminium are 3 electrons. So I need to make them equal. To make them equal, I would have to multiply this equation by 3 and the second equation by 2. That would make the number of electrons gained as 6, and the number of electrons that would be lost would be 6 as well. So I need to now write my overall equation. The overall equation, I'm going to combine the two equations, combine the reactants. So the reactants in the first equation are lead ions. So that's 3 Pb2 plus ions. And the reactant in the second equation are aluminium atoms, and they would be 2 aluminium atoms. So that would be 2Al. And in my product side, from the first reaction, the product is lead, but there would be 3 lead atoms, Pb atoms. And from the other equation, the product contains aluminium ions, but there would be 2 aluminium ions. So I've collected all my products and my reactants, and I've written this overall equation, which is going to be this, where lead ions would be gaining electrons to form lead, whereas aluminium would be getting oxidized to form aluminium ions. In the next part of the question, we now have to construct an ionic equation for the oxidation of SnCl2. So SnCl2 has Sn2 plus ions. So we're talking about the oxidation of SnCl2. So we need to find an electrode potential for the oxidation of Tin2 plus ions. So if I look at the data booklet, there's only one electrode in which Sn2 plus is losing electrons. So it's this one over here. Sn2 plus is losing electrons, and the E naught for this electrode is given as 0.15 volts. So I've copied that equation, that electrode. So Tin2 plus, we want Tin2 plus to lose electrons. For it to lose electrons, this reaction needs to go in the backward direction. Now remember that lower potential, or the negative potential, lower potential, is the one that always loses electrons. It's the one that always gets oxidized. So lower potential, we're talking about the oxidation of Tin2 plus. So lower potential would always lose electrons, and the E naught is given as 0.15 volts. So this must be the lower potential. So we're looking for another electrode whose value is going to be greater than this. So to find a value whose potential is going to be greater than 0.15 volts. So if I look at the data booklet, there are a number of potentials, electrode whose potential is greater than 0.15 volts. So let me pick just one such potential. Let's pick this fluorine. This over here, it's 2.87 volt. This is very positive. So it has a higher potential compared to the Tin2 plus, Tin4 plus electrode. So fluorine gaining 2 electrons, forming 2F minus 1 in a reversible. This is the electrode, and 2.87 volts is the electrode potential. So I've copied this equation over here, and this is the higher potential. Remember, higher potential, or the positive potential, higher potential always gains electrons, and it's going to get reduced. So it's going to gain electrons, and it's going to gain electrons in the forward direction. So between the two electrodes, this one is the lower potential, so it's going to lose electrons. This one is the higher potential, so it's going to gain electrons. So I need to now construct an overall equation for the oxidation of Tin2 plus ions. The overall equation is, I'm going to collect all the reactants. So in the first equation, Sn2 plus is the reactant. So that's Sn2 plus. Whereas in the second equation, fluorine F2 is the reactant, and my products in both half equations is, in the first one it's Tin4 plus, in the second one it's 2F minus 1. So it's Tin4 plus, and in the second it's the product is 2F minus 1. So this is an ionic equation for the oxidation of Tin2 plus, where Tin2 plus gets oxidized to Tin4 plus. So remember, higher potential, or the more positive potential, is the one that's going to gain electrons, and the lower potential, the more negative potential, is the one that's going to lose electrons. So we wanted Tin to be oxidized, we wanted Tin2 plus to be oxidized, So for its oxidation, this had to be the lower potential, and we had to pick something that had a greater potential compared to the oxidation of tin 2 plus.